We've been doing a lot with integrals, and we've even done a few applications of integrals. I'd like to talk a little bit about one of the more important applications of integrals, and that has to do with what we call rectilinear motion. You might be wondering what this word means. Basically, rectilinear just means straight line motion. If you take more math and physics classes in the future, you might hear that again. So in math, we often use y equals s of t to represent distance as a function of time. By the way, you'll also see x of t. I think that one's more used in physics, but you'll see them both. But we're going to just use s for now. Your book uses that. So then s prime is going to represent velocity, and s double prime is going to represent acceleration. Hopefully you remember that when we talked about derivatives. Now, we've done integrals, and so actually, if you have a function that represents the acceleration, you find the velocity by taking the integral of the acceleration. And you find the distance traveled by taking the integral of the velocity. We actually are going to add absolute value bars. If that confuses you right now, don't worry, we'll talk about it later. Right now, we're just you can think about it as just being the integral of velocity. We'll talk about those absolute values in like 5 minutes or so. So for my first example, I know the velocity of a particle is given as 3t squared meters per second. We want to know the distance traveled between t equals 0 and t equals 2. You're welcome to pause the video and try this on your own, by the way. So for this one, we're just going to do the derivative or the integral of v of t. And again, I did have absolute value bars in the equation up there. That will come into play when we have things that go negative. Luckily, 3t squared, if you think about the graph of like y equals 3x squared, that's always going to be either positive or 0. You're never going to have negative values. So in this case, we're not going to worry about that. So I have 3t squared dt. If I take the integral of that, the antiderivative of that, I just end up getting t to the third from 0 to 2, which gives me a value of 8. Now, I did make a note up above. Don't forget to include units in your answers. So the velocity right now is in meters per second. If I go one step up and take the distance, the over seconds go away and it just becomes meters. Actually, if you were to go one step down, take the derivative of velocity, it would end up being meters per second or meters per second squared. So just kind of keep that at the back of your mind. So this is in meters. So I just realized on the second example, I forgot to put the units, but it should be in miles per hour. And this distance right here is 1 mile. It's a really, really slow car, by the way. So we want to know if the acceleration of a car is given by a equals 6t, a of t equals 6t. You can write it with it of t, or you can just write it as a equals. We know that the velocity is 2. I'm going to say v of t equals 2 when t equals 0. Actually, better way to write that is just v of 0 equals 2. Same idea. And the distance from home is 1 when t equals 0. So we have s of 0 is equal to 1. So these are the things that they tell us so far. We want to know what is the distance from home as a function of time. So for this one, we have to do integrals twice. We are going to start by finding our velocity, and then we can find our distance. So my velocity, v of t, is going to be equal to the acceleration. You'll notice I don't actually have limits of integration. That is fine. However, this means I have an indefinite integral, so I will have a plus c. So I'm going to get t squared, I'm going to get actually 3t squared plus c for my vt. So now, before I find my distance, which I'll get by doing the integral of my velocity, I need to figure out what is that c. And I know that v of t is equal to 2 when t equals 0. So I'm just going to get that c is equal to 2. So my velocity is equal to 3t squared plus 2. Again, we have, it's a positive function. My y values of this velocity function are all positive. So we're not going to worry about that absolute value in our distance. So to find my distance, which I'm going to write as s of t, I need to do the integral of 3t squared plus 2 dt. Almost ran out of room there. And when you do that, you end up getting t cubed plus 2t plus c. Don't forget about that plus c. So we also know that s of 0 equals 1. The distance from home is 1 when t equals 0. They tell us that. So if I plug that in, I actually end up getting that my c is equal to 1. So my final answer, remember we're not going to just write c equals 1 as our answer. Final answer, I'm running out of room, sorry about that, is going to be s of t is equal to t cubed plus 2t plus 1. And for this one, we're actually not going to worry about writing units. You can write it's in miles in case you're wondering, but that's not too important at this stage. It is important for things like example number 1, though, when you're finding a specific distance. So the next thing I want to talk about is what's going to happen if you have negative values of your velocity. And in the examples 1 and 2, I did mention that your velocity functions were always positive. That's really nice when that happens. But if you get a negative velocity, which does happen frequently, that means that you're going in the opposite direction. So when that happens, the displacement and the distance traveled are not necessarily going to be the same thing. So be careful about that. I do want to mention one other thing. It's not on the printed note sheet, but that is the speed. So velocity is a vector quantity where we care about the direction. Speed is a scalar quantity, meaning we don't care about the direction. And actually my speed is going to be the absolute value of v of t. So we'll do an example where we have to worry about speed and displacement and distance. So for this, we have a velocity graph of a honeybee shown on trips from the hive to the flower garden. So the first question I asked you was describe the motion of the bee. So I'm going to I want you to pause the video and just maybe take a look at it for a minute, see if you can figure out what's going on here. So here's my honeybee picture. I'll show you like a little picture of what's going on. And I want to look at it just in like 1 to 2 minute increments. So let's look at the first 2 minutes first. In the first 2 minutes, you might notice that the velocity is going at a constant rate of 100 feet per minute. That's in the first 2 minutes. This is a really helpful graph because not only can you see that, but you can also see that the area underneath that 100 feet per minute line is 200 feet. That's actually the total distance that was gone in the first 2 minutes. So the first 2 minutes, the bee went a total of 200 feet, and the bee went at a constant rate of 100 feet per minute. I'm not going to write that out, but I'll let you write that out. The next thing that happened was this 2 to 3 minute period. After that, we can assume the B it stayed in one place for 1 minute, because that's a straight line at 0. So we can see that the bee stayed for 1 minute, probably at the flower garden. Next thing that happened was this 200 feet, this negative 100. So it's negative 100. That means it's going in the opposite direction. So what's happening then is the bee is going back. So that's another 2 minutes and another 200 feet. Again, the bee stays for 1 minute at the hive. I'm not going to write everything else out. I'm hoping you get the idea of what's going on here. But basically what this graph is showing is that when there's a positive velocity, that means the bee is going in a forward direction, which I'm assuming is from the hive to the flower garden. When there's a negative velocity, as is in red, that means the bee is going in the opposite direction. And when there's 0 velocity, that means the bee is stopped. So I'm hoping you get the idea of what's happening there. Actually, they didn't ask you to do this, but I'm just going to let you know that if you were to draw the graph of the speed, in case you're wondering, the way that would look would be, let's say this is 100, it would be positive here, and then you would have 1 minute where at 0, then it would be positive again, and then you would have another minute at 0. So it would actually be all places would have a positive line. So then it would be positive again afterwards. So it would keep on going, being positive. So that's what the difference between the... So for part B, you're asked to find the total distance traveled, and we do have this formula right here. We're going from 0 to 10, and we are looking at the absolute value of the velocity. So now the absolute value of the velocity is going to be the area under that curve, but anywhere that we have something negative, we are going to make that positive. So the first area, the one I have in yellow, that's just going to be 200. The second area, the one that's in red, that would generally be negative 200, but since we're looking for the absolute value of it, we would make it 200. So that one's actually going to become positive 200. The next area, this one right here, is positive 200. And then the next area, again, it would be negative if we weren't finding the absolute value, but we are going to make it positive. So it's going to end up being 200 plus 200 plus 200 plus 100, which is going to be 700, and it's in feet. That's our unit. The displacement of the bee, this time you are only going to be looking at the velocity without the absolute value sign. So what that's going to mean is you are going to include the negative, the ones below the x-axis is negative, so I get 200 minus 200 plus 200 minus 100. And then that gives you 100 feet. So that's telling you that after 10 minutes, the bee is exactly 100 feet from where it started from. However, the total distance that the bee traveled in those 10 minutes is 700 feet. So our last example is a little bit less practical. It's less real life. However, it's very likely that you'll see something like this on the AP exam. So I just want to make sure you can do it. For this one, we know the velocity of an object is given by t squared minus 2t. We're going to find the displacement and total distance traveled over the interval 0 to t. So remember, to find displacement, we are going to do the integral from 0 to 5 of v of t, t squared minus 2t. We just are going to calculate it as is right there. To find the distance, distance is a little bit harder. You are going to be finding the integral of the absolute value of this function. So let's do the displacement first. That one's a little easier. I am going to draw the graph of this because I think it'll be a little bit helpful, especially when we talk about distance. So this graph is a parabola that has, it has an intersection, it has an x-intercept at 0 and 2. So you can kind of see that we're going to be finding, this is not drawn to scale, by the way. You can see it's very much not to scale, but it's going to look a little bit like this. So I'm hoping you get the idea of how it looks. My displacement is just going to be the same way that you would find any other integral. You don't have to do anything special. Go ahead, pause the video and try that on your own. So displacement, I'm hoping that you got t cubed over 3 minus t squared evaluated from 0 to 5. If you work that out, you should get 50 over 3. Don't forget to put your units, which in this case is meters. The distance, unfortunately, you have to do a little bit of work before you can actually take the integral. So what we're going to do is we are going to split this integral into 2. So we're going to split the integral into 2. We're going to do the integral from 0 to 2, the place where it's negative, of this, plus the integral from 2 to 5 of this stuff. So it's really important that you split this up into 2, otherwise you're going to get a strange answer. So I want you to notice, if we look at our picture, that this is going to give us a negative area because it's below the x-axis. This one's going to give us a positive area. So the way I'm going to account for that is by, for the first one from 0 to 2, I'm actually going to take the integral. I know it's going to be negative, so once I take the integral, I am going to make it positive. So I know how to take the integral of that. I know I'm going to get a negative value. Once I get the negative, I'm going to make it positive. The second one, we know it's going to be positive, so we can take away our absolute value bars. We don't have to worry about that. So go ahead, pause the video, see if you could figure this next part out on your own. Okay, so you'll notice I have absolute value bars here, but do not let that freak you out. You're not going to really be doing anything special with this one until after you take the integral. You just know that you're going to be making it positive in the end. The second one, I get the same integral. Don't need to worry about the signs for that one because I already know it's positive. Okay, so then when I do that first integral right here, I end up getting 8/3 minus 4. Whatever I get from that, I'm going to make it positive. The second part of the integral, not too pleasant, unfortunately. I get 125/3 minus 25 minus 8/3 minus 4. So I'm going to let you calculate all of that on your own. I will tell you that for this little piece right here, you do get negative 4/3 in there. So you're going to end up making that positive 4/3. And I'll write out the next few steps. Then you get 50 plus 50 over 3. This ends up being another negative 4/3, but it becomes positive because it's a minus minus. So we end up in the end getting 58 over 3 meters. And you will notice that your distance is going to be more than your displacement. That should happen. It should either be greater than or equal to your displacement. So there's one more thing I want to mention, but it's not actually like doing math. I do want to mention that in your book on pages 508 to 509, these are pretty much the most useful pages in the entire book. Maybe not the inside and outside covers are also pretty useful because they give you the integrals, but I would, if I were you, I would either write down all of this stuff in the tables there, or at least just have it know that it's there. It basically translates every single thing you might see in one of these problems into math.